Welcome back. Our next chapter is going to be on rotational motion. So let's get started. First, there are two types of motion. Translational is the linear motion, and that's what we've been studying so far this year, where an object would move in a straight line. The other type of motion is called rotational, and this motion involves a rotation or a revolution around a fixed chosen axis. Basically, it means that something's going to rotate around in a circular type of movement. For the third fact, we need a system that defines both types of motions working together, because we're going to see how an object moving linearly would translate to something moving rotationally. And rotational quantities are usually defined with units involving a radian measure. You may have seen radians in your math classes, so we're going to touch on that a little bit in this chapter. Just like when we had linear motion, we defined our direction as positive and negative. Well, now, since things are going to be rotating, we're going to use counterclockwise, which would be moving like that, the opposite way a clock would. Counterclockwise are defined as being positive, while clockwise, moving this way, would be defined as having a negative motion. So we'll still use plus and minus signs to say which way things are rotating. Now let's define a radian. So let's consider an object that's rotating on an axis. During one revolution, that object is going to travel a distance equal to the circumference of the circle, which would be 2 pi r. A radian is defined as half pi of a revolution. That means if we were to write the circumference of a circle in terms of radians, it would be 2 pi radians. And we can abbreviate a radian with the letters R-A-D. They don't have any units. And I gave you some examples to kind of correspond to the degrees that you might be familiar with in a circle. 360 degrees would be 2 pi rad or radians, and then 180 degrees would only be pi rad or radians. And if we think about how this looks in terms of a circle, I have part of a circle drawn here for you. In other words, if we take the radius of a circle and we were to lay it down on the circumference, it would create an angle whose arc length is equal to the radius, and this tells us what a radian would be. The next thing we're going to do is look at some terms that we had talked about previously for objects that move in a straight line and define them in terms of an object rotating in this case. So we will have displacement, velocity, and acceleration. And to distinguish objects that move in a straight line for those that rotate, the ones that rotate are now going to get Greek letters as their variables. So you'll see part of the Greek alphabet show up in this chapter. So first, let's do displacement. We call this angular displacement. That means the displacement for something rotating around an axis. The actual definition is going to be the change in the angle as an object rotates. So if we think about the radius of a circle, that change in angle is going to be our angular displacement. And then we could look at a physical actual distance that an object would travel along that arc. This distance along the arc, if we were to take that and stretch it out, that would be the equivalent of a linear distance. So we can relate the linear and translational, or the straight line movement with the rotating movement, with these variables. So for rotation through an angle in radians, a point at a distance r, so a radius from the center, that object is going to move a distance d. And your formula would look like this. The d, which would be what that arc length looks like, would be equal to the radius times this displacement, which would be in radians. And for our units, you'll see meters for the distance and meters for the radius. And then when we look at the angular displacement, that would be something that we call in radians. Now let's look at how fast something can rotate. This would be called an angular velocity. Again, the word angular lets us know that we're going to be rotating. The Greek letter is a lowercase omega. It's like a curvy W. And since we have talked about velocity in the past as a rate of change in displacement, our angular velocity, all we're doing is putting this word angular into our definition. So now angular velocity is going to be the rate of change in angular displacement. So I have the comparison for you. I know this says an x right here. We had also talked about that as being a d for our displacement or distance. Translational, remember, is a straight line, so our velocity would be that change in distance or displacement over time. Now for the angular velocity or rotational velocity, we're going to say the change in angular displacement over time. So everything that we studied so far in a straight line is going to have a rotational analogy that goes with it. And lastly, for angular velocity, we can relate it to our linear velocity with the following formula. V, which is our regular velocity, is going to be the radius of a circle times the angular velocity. And let's look at the units. Remember that when we studied velocity previously, it was in meters per second. The radius of your circle should always be in meters, and our angular velocity will be in radians per second. So when we look at the equivalence, the analogy between linear and rotational, wherever you see meters, those are now going to become radians for our displacement and velocity. Now for this next section, there are other ways that we can calculate an angular velocity, so I'm just going to walk you through those steps. Typically, we would say the speed of an object would be distance over time. If something is moving in a circle, the distance that it would travel all the way around that circle would be the circumference, and then the time to go once around would be called the period. And I believe we had that earlier in the year. We'd mentioned the time for one revolution called the period. And then a friendly reminder, in case you don't remember circumference, it's 2 pi r. So instead of saying distance over time, our distance is now our circumference, and the time specifically is the period. So both of those are for once around the circle. So if we keep going, I've rearranged that and said that now velocity over radius, all I did was divide both sides by the r. That's equal to 2 pi over t. And let's see what that gets us. Okay. Remember earlier in the year we had talked about frequency. That's going to be a lowercase f. We've had that before. And frequency was the inverse of the period. So you can look back in those notes from last semester if you need to review that section. So now if we make some substitutions, angular velocity can be equal to any of these things. So it depends on what you're given. If you have radians or an angular displacement, you would say angular displacement over time. We could also rearrange that formula from the previous screen earlier and say linear velocity over radius. This is also equal to 2 pi over the period, or 2 pi times the frequency. So you have a lot of options here. And remember that the formulas will be provided for you on the test, so don't worry about memorizing all of these, but you do need to understand that the angular velocity can be equal to any of those 4 things. And then a reminder on your units, the angular velocity is radians per second, and the angular displacement will be radians now. I know we've used that theta symbol before, but this time it's going to talk about radians and not degrees. I'm going to stop there for now. In our next lesson, we'll pick up angular acceleration, and then we'll summarize and compare the linear formulas to the rotational or angular formulas.